Hey, alright. So we're finally here at Exponents. I've been wanting to talk about exponents since the Axiom video, but I felt like in order to really explain why these following facts are true, we had to go over functions because we need to go over bijective functions, meaning that only bijective functions have inverse functions, and inverse functions will come again. There's going to be one function with a specific inverse that is really important to the whole idea of exponents. Well, more or less. See, the thing about exponents, they're called the laws of exponents. I think usually is what they're referred to as. And usually when you hear a law of something, you feel like it might as well be like right up there with axioms, right? The law of gravity, right? Why is it true? It kind of just is. I mean, I think, right? So yeah, when you hear law of exponents, actually there's an explanation to them. They're not just like just things that are true just because so. Um, you very well can just make them axioms. Uh, so here's what I mean. Um, I've looked into it, and supposedly there is a way to prove these facts through calculus. I believe I know what that explanation is. I looked it up myself with the calculus book that I have back there. But it's the calculus explanation. It all boils down to one key thing, and that one key thing to me seems like, oh well, you just made it true for like as if it was an axiom. So that whole thing about the calculus explanation kind of made it just seems like, okay, all you have to take is this one thing to be true, and then everything falls into question. Um, well, I think I've looked at it at a different way in which, similarly, yeah, all you need to do is to just trust me in this one little thing. And if you can't trust me in this one little thing, then yeah, I can prove the all the laws of exponents. I mean, this as a side note, right? There's a thing called the law of sines and law of cosines. Like sine, cosine from trigonometry/geometry. I think those things, again, they're provable. They're provable facts. So again, I don't know. Maybe I'm just misreading when people say this is a law of something, and um, it's just a provable thing. But anyways, right? So in what I believe is a good explanation to why these facts are true. Again, it's only going to come down to just one thing in particular. If you can believe that, then everything else should also be believable. That being said, this one thing that I'm relying on has to do with logarithms. So again, if you did watch the whole part one and part two about bijective functions, well, we're gonna have this thing called exponential functions, and they turn out to be well, one to one in particular, which means that they're gonna have an inverse, right? The inverse of exponential functions are called logarithms. I mean, logarithms kind of, that's really what they are. They're just the inverse functions of exponentials. I mean, you can look at them in their own right as just a function that gives that when you input a number, the output is the number that you need to raise a specific base to get that input. I mean, again, you'll see when we get there, right? And you'll see why it made sense to talk about inverse functions. So I would say that that's the deal, one of three ways. First choice is that you can just take the law of exponents as just a fact, as an axiom, whatever, and we would just move on. Two, you wait for me to do the whole calculus explanation, which means that explanation won't come for a long time until we reach calculus. Or the third option is that you stick around and you see how I tend to claim to prove that, yeah, actually you can just prove them with just this one little thing. And of course, everything that we prove up until today so far. So that being said, the first video, this video is only going to be about, exponents. They're more of a way to jot down or compress information, really. Like 3 to the power 5 just means 3 times 3 times 3 times 3 times 3. So that's kind of why it's not even an action. It's kind of, the exponents are just a means to an end to compress information. That being said, it turns out that you get a lot of cool facts that makes you compress even more information, right? So this first video is just going to be all about, explaining exponents, really. And then the following videos will be about, try to prove these law of exponents. So if you're a viewer who just doesn't like explanation, if you're just a sheep, I guess, and you just want me to tell you how to do math without really knowing why these things are the way they are, if you just want to, just listen to what I say, this is how you do something, and then follow it blindly, then I guess you just have to watch this video. But if you want to see the explanation to why things are true, then hopefully you've been paying attention so far. I mean, I know this whole prologue playlist, I kind of made it like if it's the Dark Souls of mathematics, right? Like it's like I don't hold back. Trust me, I have been holding back. I've only covered the bare minimum, and yet, I'm claiming that these are videos for people that maybe are not good at math and they just wanna look at math outside of the classroom. Watching these videos doesn't depend anything about your grade. So maybe without that pressure, maybe these math ideas stick better. Alright, well, let's get into it. Let's talk about exponents. Okay, so the law of exponents, right? Law, or laws, I should say, of exponents. Well, what is an exponent, right? I haven't even said that. I mean, so this is what it is, basically, right? It's just a shorthand notation for a number being multiplied to itself multiple times. So let's say that if a is a real number, and let's say that n is a natural number, then a to the power n just means a times a times a times a, a total of n times. I mean, for example, if I say a to the power 4, I mean a times a times a times a, there's 4 a's. So that's basically what exponents are, right? I mean, that's probably how they get introduced. The particular part is this, right? A could be any number, but the power makes sense if it's a natural number. Okay. Well, I mean, let's continue, right? What are the actual laws of the exponents? So, let's see. The first law, probably the most important law, is the following: that if you have a to some power times the same number but to a different power, then the result is a to the power adding up the powers. What does that mean? I don't know, like if you have 2 to the power cube times 2 to the power 5, then you're gonna get 2 to the power 3 plus 5, 2 to the power 8, right? Which would make sense. I mean, this means that you have 3 2's, right? 2 times 2 times 2, and this means you have 5 2's, 2 times 2 times 2 times 2 times 2. So how many would you have in total? You would have 8 in total, right? Okay, so like I said, this will be the most important one out of all of them. Basically what the rest of the video is gonna talk about. But okay, let's look at another law of exponents, right? Well, the one that kind of follows this one is kind of more of a rip off, really, is this, right? If you have, let's say, a fraction, a to the power m divided by a to the power n. Well, so one solution to this is that what you have is equal to a to the power m minus n. You see, it's kind of similar. That's what I'm saying. It's a little bit of a ripoff. So what do they mean in action? Well, okay, let's suppose that you have again a 2 to the power 5 divided by a 2 to the power 3. So you have a fraction where you have 2 times 2 times 2 times 2 times 2 divided by 2 times 2 times 2, right? So let's do some advanced fraction math, right? This cancels with this cancels with that, this cancels with that, and you ended up with just 2 lefts, right? 2 times 2 over 1, which is just 2 times 2. Okay, it's just 2 square. But if you look at it, 2 square, right, it's the same thing as 2 to the power 5 minus 3, right? So 2 to the power 5 minus 3, 2 square, is the same thing. Well, so this happened because the power 5 up here was bigger than the power on the bottom, which is 2, right? I mean, what would happen if you had it the other way, right? Well, let me put it right here. Let's see. The other way that it could go is that, let's say that you have, let's just say that m is just bigger than n for no real reason, right? But if we assume now that the bigger one is in the bottom, well, now this is going to be equal to 1 over a to the power m minus n. Again, let's do a quick example, right? I mean, it would have said, I don't know, 2 to the power 3, 2 to the power 6. I don't know, I just didn't really want to do the same thing, but okay, so you have 2 times 2 times 2 over 2 times 2 times 2 times 2 times 2 times 2. And again, right, if we try to do some quick math, this cancels this cancels with that, this cancels with that, and we end up with 1 over 2 times 2 times 2. We end up with 1 over 2 cubed. And again, it wasn't really a coincidence, right? 1 over 2 cubed is exactly 1 over 2 to the power 6 minus 3. Right? So again, like I said, all these powers, all these rules of powers, they're just, the whole idea of an exponential is to make things shorter, and these things make compress information even more, right? So yeah, I mean, you can look at these two and think, so am over an is m minus n, an over am is m minus n. They're actually the same thing. We'll get to it. It's just two different ways. For example, it's two different ways of writing the same thing. All right, let's continue. What's another rule? So if you have a number, let's see, a to the power n, and then you raise it to the power m, then it's going to be equal to a to the power n times m, right? So far we had addition and subtraction, now we have multiplication, right? I mean, what does this rule say? It says that if you have, I don't know, 2 to the power 2, and then raised to the power 3. Well, looking at this notation, 2 to the power 2 to the power 3 has to mean one thing, that you have, basically you do kind of like the exponent. You can do this exponent first and then do that exponent. What I'm trying to say is this, right? This is 2 squared and then cube. So if I try to undo this power first, I need to do 3 of these ones, right? So I should have 2 squared times 2 squared times 2 squared, right? And then now if I try to undo these ones, then I have a 2 times a 2, 2 times a 2, 2 times a 2. So what am I going to have in total? 1, 2, 3, 4, 5, 6. I'm going to have 6 2's, right? And that's kind of what this rule is saying. I have 2 to the power 2 times 3. I wonder if I should keep using 2, since I'm using that as my A as N as my N. Maybe I shouldn't be doing that, right? But again, this process right here is kind of really what it explains. You know, you have a repeated n times, but then you're gonna repeat it m times in the same way that you have 2 square, but you have it 3 times, so 2 squared, 2 squared, 2 squared. I hope it's kind of clear why it turns out to be multiplication, right? I don't know. Well, something similar happens over here. This OR rule. Now suppose that you have 2 different numbers but only one power. So if you have a times b to the power n, well, this is going to be equal to a to the power n times b to the power n. Alright, suppose maybe we have I don't know, 2 times 5 to the power 3. Well, again, if I'm trying to undo the power, because, you know, powers are kind of annoying when they're on top of parentheses. Well, this should just mean 2 times 5, 2 times 5, 2 times 5, right? Well, so I have 2 times a 5 times a 2 times a 5 times a 2 times a 5. Why did I do it this way? It's because, again, one of the axioms, see, I mean, axioms, the whole axiom video matters. One of the axioms is that I can actually shuffle the numbers however I want them. Well, if I do enough shuffling, you'll see that I can shuffle them enough to where I have 2 times 2 times 2, and then 5 times 5 times 5. But then what do I have now? I have 2 cubed times 5 cubed. And again, that's what this rule is saying, right? A times b to the power n equals a to the n times b to the n. I guess there's one more. There should be 6 in total. 1, 2, 3, 4, 5. Yeah. Well, I guess I would say the next one is kind of the ripoff of this one. Is now suppose that you have a fraction. So a over b to the power n is going to be a to the n over b to the n. So I'm just going to do 2 and 5, right? So 2 over 5 to the power 3, right? So again, in order for me to undo this power, I just have to do it 3 times. 2 over 5 times 2 over 5 times 2 over 5. And I'm glad that I also did the video about fractions, right? Because that's the one thing I said. Multiplying fractions is the easy part. You multiply the top with the top and the bottom with the bottom. So if you multiply 2 at a time and then multiply the result to the third one, or you can just multiply all of them all together, you know that the numerator is going to be 2 times 2 times 2, which is going to be 2 cubed, and the denominator is going to be 5 times 5 times 5, which is 5 cubed. So again, right, a over b to the power n is a to the n over b to the n, as we see. Like I said, these are all I showed you so far are just examples. They're not proofs by any manner. But again, right, when you're introduced to this law of exponents, that your teacher introduces you that these statements are true, but mainly they only show you for natural numbers, right? What I'm trying to say is that not only can a be a real number, but n can also be a real number, and these 6 facts still hold. You know, like if I had, for example, if for whatever reason I had 2 to the power pi times 3 to the power pi, like I said, I really wouldn't know how to explain that to you. But I'm telling you that and again, these things, remember, equations go back and forth, right? They're not just if here then there. You can also go from here to there, right? So if I'm saying 2 to the power pi times 2 to the power pi, I'm saying, yeah, this will be a logical thing to say that this is 2 times 3 to the power pi, or rather 6 to the power pi. You know, but again, right? Unless I actually prove that these statements can hold for real numbers, not just natural numbers, then I can't really say this just yet, right? Okay. By the way, I guess one thing I should have noted is that even though I'm saying that, well, for this part, for this definition is correct, but I believe that for some of these to work, I think sometimes we restrict them to where the base, the A and the B, can only be positive numbers. It's kind of like a case by case basis. We'll see. Well, I mean, I wanna see how far I can get, because it looks like I'm doing kind of okay time now. See, okay, so if A is a real number and N is a natural number, we think that we know what A to the power N means, right? So let's keep A being a real number, but then what if N is an integer, right? Well, do they still hold, right? Well, what even is A to the N? So what is A to the N if N is an integer? Well, what are integers? They're like whole numbers, right? 1, 2, 3, 4, 5. So okay, natural numbers, but then they also include 0, and then they also include negative numbers, right? So I guess at this point I'm really asking, what's a number raised to a negative power? Now the axioms kind of stated, okay, well, A to the negative 1 is just 1 over A, right? And you could say that this is so because we're trying to say inverse, right? But now that we have a whole new set of rules about laws of exponents, why should this continue to be so, right? Well, like I said, I'm gonna say right here again, the biggest motivator for this video is gonna be that we really want this to work. A to the N times A to the M is A to the N plus M. This is going to be the one rule that we definitely want to be true. So then, if you have, for example, say you multiply, I don't know, A cubed times 1 over A, right? Suppose that you don't agree that 1 over A is A to the power negative 1, and we say, okay, we're gonna say 1 over A is A to some mystery power. So since I'm saying mystery power, I'm just gonna say, I don't know, X, right? So say that 1 over A is A to some mystery power. Okay, what do we know, right? We do know, however, that if we multiply A cubed times 1 over A, so you're multiplying A times A times A over 1, let's say, times a 1 over A. So what's gonna happen? If you do the math, let's say that this A cancels with this A, and the result is that you're gonna have 2 A's on the top, and let's say a 1 on the bottom. Again, when I say cancel, this isn't really proper, right? But actually, when you cancel something, the thing that gets canceled, you should see as if it's being replaced by a 1. So that's what I'm saying. A 1 times a 1, and then A times 1 times 1, and that's what we got, A times A over 1. Which is A squared. Okay, so if we really want this rule to work, right, A cubed times 1 over A equals this. This needs to be equal, apparently, this needs to be equal to A squared. So what am I saying? I'm saying that 3 plus X needs to be equal to 2, right? Because A cubed times AX, if we really want this to be true, then this is going to be A to the power 3 plus X. And over here, when we do the math, we know that the result needs to be A squared, right? So I'm saying, because I want A to the power 3 plus X to be equal to A to the power 2, I'm really saying I want 3X to be 3 plus X to be equal to 2. And if you solve this, how would you solve this? Well, so it's an equation. So again, in the axioms video, we know that you can add or subtract the same number from both sides. If we subtract 3, or if we add the negative 3 to both sides, we get that x equals 2 plus a negative 3. What's 2 plus negative 3? Negative 1. So then, yeah, right, then x equals negative 1. So then if 1 over a equals a to the power x, then x has to be negative 1. So yeah, we were right to assume that 1 over a is a to the power negative 1. Okay? Well, what does this mean for the future? Like I said, we really want this formula to work. So for example, say that say that m is a negative number. How do we say this? Say that m equals negative n, where you definitely know that n is a natural number, right? So if we say that n is a natural number, then if we say m equals negative n, it just means a negative number, right? Like negative 1, negative 2, negative 3, negative 4. So in this situation, we're saying a to a negative power, okay, just means a to, so let's see, right? What would make sense for a to the negative 3 to be, right? Or I don't know, 5 to the power negative 3, right? What would it make sense for this to be? Well, I guess I forgot to say something, right? So the fact that 1 over a is a to the negative 1 poses an interesting idea. If 1 over a equals a to the negative 1, then a times 1 over a, right? A times a to the power negative 1. Well, these two things are the same, right? They're equal to 1. If you go by the definition that I gave you, a to the n is just a times a times a n times, then a to the power 1 is just a, right? So then this a right here is just a to the power positive 1. But then what am I saying now? A to the power positive 1 times a to the power negative 1 equals 1. So I'm saying a to the power 1 plus negative 1 equals 1. What I'm really saying is that a to the power 0 is 1. So this is going to be a special rule, right? A to the power 0 is 1. And if that doesn't sound convincing, because again, like I said, I am being honest, right? I'm just really trying to make this work. Well, trust me that in the future, I will give you a better, a more convincing explanation to why you should accept the fact that a to the power 0 is 1. Basically, for any number, I think. Maybe not 0 though. We'll get to this, right? So a little disclaimer on the side. Okay, so I really should have cleared that up first, right? Because a times 1 over a equals 1. Well, that means a times a inverse is 1. Or another way to look at it, a to the power 1 times a to the power negative 1 is 1. This forces a to the power 0 to be 1 if we really want this to work. Okay, so now that being said, right, a to the power negative 3, right? Well, what's something that's going to be true about this? A to the power negative 3 times a to the power positive 3 should end up a to the power 0, which is 1, right? Well, what kind of number can you multiply to a cube so that you get 1, right? Basically, you're saying, what's the multiplicative inverse of a cube? Well, I guess what I'm saying is that, the only way, well, not the only way, but the only way to turn a cube to a 1 is if you multiply 1 over a, 1 over a, 1 over a 3 times, right? So I'm saying a cube, right, times 1 over a cube. Yeah, that makes sense, right? This makes sense. But this is that, right? But this is a cube times basically a inverse 3 times. This is kind of the point that I really wanted to make, right? This kind of like this connection, and it goes this way. You look from here to here, and then you look from here to here, right? I think that makes sense. So what I was gonna try to say over here is that, okay, if a is a to the power m, which is just really a to the power negative n for some natural number, well, you can look at this as being a inverse n times. But what does that eventually mean? That just means 1 over a n times. And then what is this going to mean? 1 over a times 1 over a times 1 over a n times 1 over a times 1 over a. So what is that going to mean? It's just going to be 1 over a to the n. Alright, so let me just write over here, right? One more time, a to the power m, or just really this, a to the power negative n. It's going to be a inverse n times, which is really going to be 1 over a n times. Again, 1 over a, a total of n times. And you multiply a bunch of ones on the top, you're gonna get a 1. You multiply a times a times a on the bottom n times, you're gonna get a to the n. So that's what I'm saying, really. A to the power negative n just means 1 over a to the n, right? Alright, I mean, if that didn't make sense, I mean, just leave it in the comments. Maybe I can explain it a different way. I look at the clock and I get nervous. So what do we have so far, though, right? If n is a positive number, a natural number, we know what a to the power n is. Okay, suppose it's not a positive number, suppose it's 0. Well, we know what a to the power 0 is. It's just 1 for any number except 0. I guess I should, again, add this disclaimer, right? And what if n is just a negative number? What if m is just negative natural number? Well, you know, logic will follow that it's just 1 over a to the n. I mean, I guess that was what I was trying to say here. 5 to the power negative 3 is just, well, if you know that 5 to the power negative 3 times 5 cubed equals to 1, the only number that's going to make it is going to be this, right? That's the multiplicative inverse of 5 cubed, 1 over 5 cubed. I guess that's the best way to put it. Let's just move on, right? But what I'm saying now is that we achieved a new goal. If, let's say, now it's an integer, then now we know what a to the n is. Understood, let's say. Okay, so now we know what powers mean for natural numbers. Now we know what powers mean for integers. Well, what's the next step? What does a power mean when you have, let's say, a rational number, right? So yeah, what if m is now a rational number, right? And in other words, what if m is a fraction, p over q, where p and q are both integers, and of course q is not 0, right? So I don't know. So now I'm saying what's 5 to the power 3/4, right? How can we make sense of that? What's 5 to the power 3/4? Well, let me put it like this, right? Well, 3/4 is just, I mean, 3/4, right? Like I said, I can explain this in the fraction video, right? Wouldn't it just be 1/4 plus 1/4 plus 1/4, right? That's what we call the top number, the numerator. It just tells you how many they are, right? So basically 5 to the power 3/4 is 5 to the power 1/4 plus 1/4 plus 1/4. And again, I really want this formula to work. So then, how do I break this up? This just means 5 to the power 1/4 times 5 to the power 1/4 times 5 to the power 1/4. So then, if I can kind of do this probably with just any fraction, right, or any rational number that I can, you know, the numerator just tells me how much of them they are. I guess what I'm saying is, oh, look at this. This is kind of slick, right? I have 5 to the power 1/4 3 times, right? 5 to the power 1/4 3 times. So wouldn't it just be 5 to the power 1/4 parentheses cube Right? I think that was slick. But that's what I'm saying. Okay, so a number to the power p over q, to me, I'm guessing it's just going to be a number to the power 1 over q, and then raised to the power p, basically. I mean, again, just like what happened with this 5, right? 5 to the power 3/4 equals this, equals that, equals that. So I'm guessing that this is a good way to start. A to the power p over q is just going to be a to the power 1 over q, then to the power p. So I'm saying the p doesn't even matter. Now I just really need to ask myself, what is a to the power 1 over q if, let's say, q is a positive number? We'll worry about the negative later, I suppose. Right? What's a number 1 to raise to the power 1 over q if q is a natural number? Well, you probably know this from your algebra class, right? Like, for example, what's gonna be 5 to the power 1/2? Well, how can we make sense of this, right? Well, you know this, 5 to the 1/2. If we really want this to make sense, right? 5 to the 1/2 times 5 to the 1/2 is going to be 5 to the power 1/2 plus 1/2. 1/2 plus 1/2 should be 1. So 5 to the power 1. So 5. So what I'm saying is 5 to the power 1/2 is going to be some number, so that when you multiply it to itself, you get 5. 5 to the power 1/2 times 5 to the power 1/2 equals 5. So a number that you multiply to itself equals 5. If that doesn't ring a bell, then I'm just going to say it out loud. 5 to the power 1/2 is going to be square root of 5, right? Because square root of 5 times square root of 5 better give you 5. So yeah, 5 to the power 1/2 is going to be just square root of 5, right? Do you see kind of where I'm going? 5 to the power 1/3, right? Well, you know, it better be true that 5 to the power 1/3 times 5 to the power 1/3 times 5 to the power 1/3, it better be the case that this equals 5. So then what makes sense that 5 to the power 1/3 is the cube root of 5. And if you can see that this logic makes sense, right? Then you can just say in general maybe that a to the power 1 over q is just gonna mean the cube root of a. And as an extension of that, a to the power p over q is just gonna mean the cube root of a raised to the power p. Again, I'm pressed on time. I really don't like giving you guys 40-minute videos, but I think that's making sense, right? So we have kind of figured out another big step. So if p over q is a rational number, then we understand what a to the power p over q is. So a to the power p over q is understood. Again, if it's not understood, just leave a comment, guys. I'll try to explain it better, right? So I mean, I think we've come a long way, though, right? We started this video saying, you know, what are exponentials for nice positive numbers, nice whole positive numbers. Now we know what exponentials are for rationals, right? So I guess here's the big step now, right? If we're gonna make sure that these exponential rules make sense for the real numbers, right? Then now we've come at an impasse, right? In order we can say that we know what it means for any real number, then we gotta take care of the irrational numbers, right? So if m is irrational, if m is in the real numbers, but m is not in the rational. So basically that's what irrational means, that you are in the real numbers, but that you're not a rational number. Then what is a to the power m, right? So okay, this is the best I can do, right? Because again, in order for me to actually give you proof, that's going to be probably the next video where we talk about the functions, which is why I had to talk about bijective functions. So here's the only thing I can explain, right? How can I explain what 3 to the power square root of 2 is? What's 3 to the power pi? Right? Well, I think I can actually get very close to explaining what they are. I mean, let me put it this way, right? Square root of 2 is equal to 1.4142. Okay, that's as far as I know. 1, 3, 5, 6, 2, 4. And again, it's infinite, right? So I'm just gonna stop there, right? And then pi itself is 314, 15, 9, 26. That's honestly, as far as I know, 535. Right? Okay. So again, notice that again, the fact that they're rational, I can only give you like, you know, a truncated version of what the true value is, right? So what am I saying? So what's 3 to the power square root of 2? Well, this should be equal to 3 to the power 1.4142, 1, 3, 5, 6, 2, 4, etc. Right? Okay, how does that help me? Well, I can kind of break this apart, can I? This will be 3 to the power 1 plus 0.4 plus 0.01 plus 0.004 plus 0.0002 plus 0.00001. I don't know, I guess I'll probably just end it there too, right? Okay, so what does that mean? Well, I have 3 to the power 1. 0.4 is 4 out of 10. 0.01 just means 1 out of 100. 0.004 means 4 out of 1,000. 2 means 2 out of, which is one more 0. Okay, 10, 100, 1,000, 10,000. And so on, right? Next one is going to be 1 over 100,000. And I could keep this going, right? So this will be 3 to the power 1 times 3 to the power 4 over 10 times 3 to the power 1 over 100 times 3 to the power 4 over 1,000 times 3 to the power 2 over 10,000 times 3 to the power 1 over 100,000. And I could continue to approximate this more if I really wanted to, right? So what I'm saying is that 3 to the power square root of 2, you can, yeah, the more you approximate square root of 2, the more you approximate 3 to the power square root of 2, right? If you say, oh, square root of 2, that thing is just about 1.41. Then you have to admit at that point that 3 to the power square root of 2 is about 3 to the power 1, I suppose, times 3 to the power 4 over 10 times 3 to the power 1 over 100, right? And again, if you decide you want to approximate square root of 2 even more, 1.4142, then you can also approximate 3 to the power square root of 2 even more, right? 3 to the power 1, so it's just 3, times 3 to the power 4 over 10, times 3 to the power 1 over 100, times 3 to the power 4 over 1,000, times 10,000. Alright, whatever, right? Yeah, what I'm saying is that just because just because you don't know exactly what square root 2 means, the fact that you have to approximate doesn't make it any less real, right? Well, if that doesn't make it any less real, then 3 to the power square root 2 doesn't make it any less real either, right? The more you approximate square root 2, the more you can approximate 3 to the power square root 2. So you'll see that it exists, like if you actually try to approximate it even more every time, you will see that it is actually approaching a number. Like it's not a different number every single time. It's actually getting closer and closer to a number. Again, the full explanation to that will be analysis, I guess, slash calculus, but now it's mostly analysis, right? So yeah, this is how you make sense of irrational numbers, This is how you would make sense of, again, 3 to the power pi if you wanted to. You can find what that is, or you can, or rather, you can approximate what it is. The more you approximate pi, but if you admit that pi is a number, then you should admit that 3 to the power pi is also a number. I don't know. So yeah, right. So like I said, what was the point of the video? Well, the point of it is that at first I wanted to give you the law of exponents, which I did at the beginning, and then as a kind of like an IOU, I'm telling you, this applies even when the powers are not natural numbers, right? And then the second point was to actually explain, well, try to rationalize what these, what 2 to the power an integer, what 2 to the power irrational, what 2 to the power an irrational means, So again, the next videos will be about actually trying to prove, or I mean, giving you an explanation to why these laws apply for all real numbers, not just natural numbers. I mean, again, why are they playing for natural numbers in the first place? I haven't introduced what a proof by induction is. That would be like the proper way to prove it. Instead, I just gave you examples, and I'm getting the feeling that, again, if you're watching this, if you truly are, not that good at math, but you've stuck to the videos, then I think you probably do like the examples better than some type of explanation that I can provide. But okay, so now we know about exponentials. They're important because they help you out with manipulations. Again, compacting information into smaller, easier to handle form. Alright, I'll shut up for real now because it's way too long now. And hopefully you watch the next videos. Hopefully you're interested in some type of explanation. But if not, now I think you have all the power you need to not be afraid of algebra. Okay? Well, if you like this, leave a like, leave a comment, subscribe, all that good stuff. See you next time.